Let us resume our discussion on low Reynolds number flows, and uh, towards the end of last lecture we were looking at our dimensionless Navier-Stokes equation. So, let us say we have this. So, let us include the Euler number here. Okay. So, we had made a remark that Euler number, which is P naught over rho u square, where these are the scales. Okay, these are not the fields that we are talking about, these are the scales of pressure, velocity. Density is anyways constant in our incompressible flow discussion, so it does not matter. Okay. So, P naught over rho u square, okay, this you take it as 1 when when pressure or P naught equals rho u square or pressure changes are due to inertia of the flow. Okay. So, for example, let us say there is a flow that is hitting a plate. Okay. There is a flow that is hitting a plate or a wall, and the flow has a speed u with fluid density rho, and it is becoming stagnant at some point, and it may be going like this. So, in these kind of cases you would expect that the pressure changes. So, at infinity the pressure is, let us say, P infinity or atmospheric. You would expect that the pressure close to the plate will have variations from P infinity of order rho u square, which means here that let us say rho is 1 kg per meter cube, velocity is 10 meters per second. Okay, then you would have of order 100 Pascal pressure changes. Okay, that is what we mean, that pressure will be, let us say, pressure changes, not absolute pressure I am talking about. The pressure changes will be of the order of rho u square in these kind of scenarios. However, if you have a scenario like this where you have a flow that is happening and you have walls here, then we have solved this kind of a flow, and you saw that pressure balances the viscous forces in this situation. The inertia does not play any role for different reasons, for the reasons for the assumptions that we made unidirectional and all those things. Because of those, all the left hand side terms of our Navier-Stokes equation dropped out. What does it mean when the left hand side equations, left hand side terms of this Navier-Stokes equation, momentum equation, drop out? What it means is that inertia plays no role. Okay, because if you compare it, this is essentially, so in the dimensional form, this is rho d du by dt, which is acceleration of a fluid particle, equals minus grad p plus mu del square u. Okay. So, what happens is when you have low Reynolds number steady flows, these terms actually, the terms on the left hand side drop out, which signify inertia. This is mass into acceleration per unit volume. Okay. Basically what you are saying is that the flow is so slow compared to some time scales, the flow is happening so slowly that a fluid particle, as it moves at different positions, the inertia of the fluid particle plays no role in its rate of deformation. The only things that play a role are these forces, and these forces balance each other out. Okay. So, the inertia of the fluid particle plays no role. So, usually Stokes flows or low Reynolds number flows are also termed like non inertial flows or inertia less flows in some textbooks. The idea is to emphasize that the inertial terms play no role. The inertia of a fluid particle plays no role. The forces are balanced. There is no acceleration of the fluid particle. There is no acceleration of the fluid particle. Okay. Do not straight ahead assume that this is a steady flow, this must be a steady flow. It is not just steady flow, this whole du by dt, the material derivative of velocity, is 0, or it can be neglected. It is not 0, it can be neglected. That is the idea. So, this happens when you have pressure changes due to inertia. Euler number is 1, but in other cases when you take pressure scale to be mu u naught over L, then you will get something like mu u naught over L over, or mu u over L, mu u over L rho u square. This gives you 1 by Re. Okay. So, this is the situation that happens in your Stokes flows. The idea is that pressure is balancing viscous stresses. So, of course, the correct scale for pressure is a viscous stress scale, not the inertial scale. Okay, not the inertial scale.
Example also, finally the pressure is balancing the viscous forces.
There is no balance between pressure and viscous forces, because you cannot say that all the nonlinear terms are 0. The rho du by dt is not necessarily 0. You cannot ignore that.
No, in the bottom case.
This one, no? Yeah, so this is the example of that a case where pressure is balancing viscous forces. And this is the example where you saw that all the left hand side terms went 0. When we looked at flow in a channel, the pressure driven flow in a channel, what were the governing equations that we obtained? In the momentum, the x momentum equation simplified to this, right? The x momentum equation simplified to this: viscous stress forces balancing the pressure forces.
So when is P not equal to mu u by L?
अरे यार यही तो कहानी है पूरी. What do you mean when is it equal to? It depends. So okay, no, so the thing is, first of all, P naught is not a variable of the flow. Okay, P naught is a scale that you're choosing to non-dimensionalize your governing equations. So P naught being this or this, rho u square or this, is a choice. Okay, and what I'm saying is that the correct choice of mu u by L, or the choice of mu u by L is correct when pressure forces are balancing viscous forces. So you have to have a physical intuition of what is going on in the flow. Okay, or you need to know what assumptions you are making and see if your left hand side becomes 0 in the momentum equation. Either of these two, you need to know that. Okay.
So in this case, what exactly is happening? Flow is going on
Which,
above,
this one?
above this.
So what's happening is that there is a plate and there is a flow from infinity, uniform flow of velocity u naught that is coming, and it is getting diverted by the plate like this. This is called a stagnation point flow. Okay, this is a very standard flow, a stagnation point flow, because there is a stagnation point that is formed at the center where the velocity becomes 0 and you have a pressure. So if you assume inviscid flow up to here, you can apply the Bernoulli's equation, but we'll discuss that later on. Okay, you can apply the Bernoulli's equation and basically obtain the fact that obtain this, that pressure changes will be of order rho u square. So this is the correct choice when pressure forces balance viscous forces. And in that case, we see that the equation, the dimensionless equation becomes minus del star p star plus del star square u star minus Re del or du star over dt star equals 0. Of course, the continuity equation is always there. So, if there is still a confusion of why this choice is correct, okay, you should read the textbook more, and basically this is after building an intuition of what is happening in the fluid flows. Okay, you can make the wrong choice, you can go ahead and solve the equation, you can obtain a result just to conclude that this result means nothing, this result is meaningless. So there is a little bit of, you may think that there is a little bit of trickery going on here. Why did you pick pick this as the correct scale of pressure and all those things? But you can try otherwise and eliminate that choice if you want.
valid for the Stokes law.
Hmm?
This choice.
Yeah, this choice is valid for the Stokes flow, where the flow is basically the pressure forces are balancing the viscous forces. So, we end up with this equation and then we say that my u star is some u naught. So, I was writing subscript 0 in the last lecture. I just do not want to confuse you with this p naught and everything. So, we assume these to be the asymptotic expansions. So, this is a standard trick of solving an equation where you have a small parameter which is this R e. Okay. This R e is much less than 1. So, where you have this small parameter R e, this is a standard trick, and then we are going to deal with just the leading order equations, and the leading order equations give us that del star of this P 0 equals del star square u 0. You can convert this back to dimensional form and obtain. So, this is the non-dimensional form. Okay. The dimensional form will be simply grad of P equals mu del square u, with the understanding that del dot u is 0 obviously. So, these are the governing equations for your low RE flows, to be specific steady low RE flows. Okay, to be specific steady low Reynolds number flows. You could also have unsteady low Reynolds number flows. You could also have unsteady low Reynolds number flows. Okay, and I would leave this as an exercise to you. So, in this non-dimensionalization, we took the time scale. So, if you remember, T star was defined as T times U over L. So, we took the time scale as the time scale of the flow. If there is a flow of velocity u or speed u, then we took the time scale as L by u. Okay. But what if there is a scenario where there is an externally imposed time scale? For instance, let us say you have a sphere in a flow of speed u naught, and this sphere is oscillating with some frequency omega. In this case, your time scale, the correct time scale to pick for non-dimensionalization is not necessarily u naught by L, or let us say the radius is r, so u naught by r, but you can also non-dimensionalize using this omega. Okay, and under certain conditions, okay, I would leave those conditions to be derived by you. Under certain conditions, you can end up with the unsteady term in this equation, just the unsteady term, rest all remains same. So, under certain conditions, so I will leave these conditions to be derived by you. These are very simple to derive actually, if you follow the non-dimensionalization and bring some non-dimensional numbers here. So, there will be an additional non-dimensional number there, and under certain conditions on that number, you will see that the equation for this kind of a flow in the low Reynolds number regime is this guy with del dot u equals 0. So, this is the unsteady low RE flow. Okay. This is the unsteady low Reynolds number flow, where you could have an externally imposed time scale which keeps this unsteady term into the picture. Okay. To even further improve this intuition, I would say that focus on this statement, that the correct choice of pressure that we are using, so this choice of pressure scale mu u by L is correct when the pressure forces balance viscous forces. It's like choosing a regime. We are choosing a regime under which we are analyzing the flow problem. There could be a scenario where flow is hitting a sphere and pressure scale is not equal to mu u naught by L. Okay, we are choosing to analyze in a scenario where pressure scale is equal to mu u naught by L. Okay, and we obtain the fact that in that scenario, if we make the assumption that Re is much less than 1, then this is the governing equation we get. Okay. So, the governing equation overall is the momentum equation. We are deriving some approximations to that under certain regimes. Okay. So, this is very simple, similar to, let us say you have this as an equation, and I am asking you to solve for its solution. I am asking you to solve for this equation solution in different regimes of B. B may be much smaller than 1, B may be much larger than 1, B may be similar to 1. This guy. So, what I am saying is, I mean, I like to go back to that example every time. What I am saying is that you can consider that your solution will be something like this, not polynomial. This is an asymptotic expansion or a power series expansion you can think of. So, what I am saying is that if let us say b is much less than 1, so you have this as your equation, then you can say that x is x naught plus epsilon x1 plus epsilon square x2 and so on, and find these corrections. Okay. What you should look at this equation as is, this is x square plus 1 with some correction. So, the solution of this equation should be the solution of x square plus 1 equals 0 with some corrections. Okay. It is like there is a governing equation, you are perturbing it a little bit. So, you expect that the solution will also perturb a little bit, and that is what we call, this is what we call as asymptotic expansion, and this is what I am denoting here for u star and p star. Yeah. Yes. Plus minus I. Mm-hmm. So, x will be plus minus I plus some epsilon times a correction. There could be, huh? So you can find that out. You substitute this here, you can find it out. What is x square? What is x square? If you write this as the sorry, this is x2. If you write this as the expansion, then what is x square? X square is x naught square plus epsilon square x1 square plus 2 epsilon x naught x1, so on and so forth. You substitute this here, so you will get x naught square plus 1 plus epsilon times x naught plus 2 x naught x1 plus higher order terms. You can individually solve these equations to find what x1, x2, x3 will be, and they are finer and finer and finer corrections to the solution of this equation. Okay. So, you can solve this guy, then you can say that this is there, and you can formulate higher order equations, all other hierarchies, and you can obtain the corrections. Okay. And that is what I am doing here, and this is something that we will be doing a lot in this course. This is standard asymptotics, and we will be doing this a lot.
Analysis on the left, you haven't assumed the flow to be steady from the beginning.
No, I have not assumed the flow to be steady from the beginning. I have just said that the time scale is this, okay, and we obtain this. What I am saying is, you may have an externally imposed time scale which could result in this term not getting eliminated, and then you will end up with the unsteady Stokes equation. Here I have not assumed anything about flow being steady. It just turns out with the non-dimensionalization that we did, we end up neglecting that unsteady term along with this convective term.
Higher order solution as well.
There you will have other terms as well, and there you, in order to solve them, you may have to assume that the flow is steady from the beginning. Otherwise, or you will end up with a Navier-Stokes equation to solve.
Because order one solution assumes that the flow is steady, that's why higher order solution should also.
No, 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 that's not necessary at all. These higher order corrections u1 p1 u2 p2, they could have time, they could be functions of time as well. Okay, for that you need to look at the specific problem that we are dealing with. We have not assumed anything about u star and p star being steady, no assumption like that. Okay, so maybe we'll do an example of this after we discuss all the examples of this particular case. Okay, first let us maybe in some physical scenarios or physical applications, where are these flows encountered. So, flows of very small microorganisms, for example, okay, flow caused by microorganisms that are trying to swim in a fluid, they are low Reynolds number flows. Okay. When you have sedimentation of particles in a suspension, it is happening very slowly. The flow induced by that sedimentation is a low Reynolds number flow. Okay. When you have flow in very thin gaps, for example, maybe some of you have seen lubrication of gears, some of you have seen that grease between two gears. Okay. The flow of that grease when the gear teeth are grinding with each other, that flow is a low Reynolds number flow. Okay. So, flows in thin gaps, flows due to very small particles, all of these are examples of low Reynolds number flows. And you can think about it very easily also, you can build an intuition. Notice the words I am using: flow in thin gaps, flow due to small particles. The length scales are small. If the length scales are very small, I am implying that the Reynolds number is small, which is rho ul by mu. Okay. So, let us first look at steady Stokes flows and a few examples of that. So, we have these as our governing equations. So, one thing straightforwardly you can see is that these are linear equations. Okay. So, you can superimpose different Stokes flows to formulate new type of Stokes flows. Okay. You can superimpose different flows to form new flows. The other thing is, let us take a divergence of this equation. What do we get? We get del square p equals mu del square of del dot u. This is what you will get, which is 0. So, pressure is governed by Laplacian equation. So, pressure is also governed by a linear equation. Okay. So, indeed you can find new flow velocities by superimposing, and you can also superimpose the pressures. Okay. As we move down in the course, we will see that not all flows which have governing equations as linear. Okay. You need to check if the governing equation for pressure is also linear, basically that is what I am trying to say. You cannot just add both the flow velocity and pressure of two flows and formulate a new flow in all scenarios. Here it just turns out that the pressure is also governed by a linear equation, so you can do the superimposition. Okay. Let us take a curl of this. What do we get when we take a curl? So, this term drops out and we get that del square of omega is 0, or del cross. So, this omega is del cross u basically. Okay. So, vorticity is governed by a Laplacian equation. Okay. Vorticity is governed by a Laplacian equation. Another interesting thing about these Stokes flows is that if you, so if velocity is reversed, if velocity is reversed, that is u is replaced by minus of u, okay, u is replaced by minus of u, and let us say geometry is mirrored, that is x goes to minus of x, then again this equation will be satisfied. Okay, there will be a minus term here due to u, there will be a minus term here due to gradient. What it means is that if you have a Stokes flow, if you look in the mirror, the flow in the mirror is also Stokes flow. Okay, if you have a Stokes flow, the flow in mirror is also Stokes flow. The other way to think about it is that if you, let us say, have a symmetric body and you have a Stokes flow past this symmetric body, you look in the mirror, what do you see? You see this as the front, right? Let us say you put a mirror here, you see this as the front, and the flow will be basically, instead of going like this, the flow will be going like this. Okay. So, if you have a symmetric body, the flow is symmetric upstream and downstream of the body. The Stokes flow is symmetric upstream and downstream of the body, because if you do these transformations, the equations remain the same. Okay. And that should tell you, so you probably have an intuition that when you have a flow past a sphere, there will be something happening here. If you remember your AMP 262 experiments, for cylinders at least, you saw that there were some vortex streets, there was some vortex shedding past the cylinder. Okay, if you remember that flow visualization experiment, when you put a cylinder in a flow, then you see that there is some vortex shedding behind that cylinder. Okay, the flow is not symmetric upstream and downstream of the cylinder. So, that is not a low Reynolds number flow. Okay. Or the other conclusion that you can derive is that there is no wake in low RE flows. What this means is that the body is present and the effect of body is symmetric upstream and downstream. There is no difference between the flow downstream of the body and upstream of the body. There is no wake that is formed. Okay, the wake is usually this deficit in velocity. Let us say you have a flow that is coming, a uniform flow hitting a body, and then after this body you will see the flow having you will see the flow having velocity profile like this. Okay, this deficit in the flow compared to its value upstream of the body is called the wake. So, there is no wake in the flow in the low Reynolds number flows. So, I really recommend you to go back and watch this fluid mechanics films on these kind of flows. Okay, these are very nice experimental demonstrations of different type of flow regimes, and there is a one whole film dedicated to low Reynolds number flows. And by looking at those flows, you will get an intuition of what is going on here. Okay, in in practice, you may have seen a low Reynolds number flow, you may not have seen a low Reynolds number flow, but by looking at those films, you can definitely build an intuition. Maybe some of you have poured honey into a container, that drop of that string of honey that forms and the coiling that happens, that can be described by Stokes flow. It can, you can think of it as a Stokes flow or a low Reynolds number flow. Okay. Now, there is an important tool that helps us solve these Stokes flows, at least in some particular scenarios, and that is the stream function. Have you guys looked at stream function earlier? Stream function has been covered in APL 106 or the introductory fluid mechanics courses for you guys. So, let us say in Cartesian 2D flows, so 2D planar flows, you have velocity as let us say u I cap plus v j cap, and then you define this u such that this is del psi by del y, you define v as minus del psi by del x. So, by this definition, by this very definition, you impose that del dot u is 0. By the very definition of velocity using stream function, you impose that it satisfies the continuity equation. So, by defining velocity in terms of a stream function, you are already satisfying the continuity equation. Okay. In more complicated scenarios, the way to think about it is you define a stream function such that del dot u is 0. So, for example, this del dot could be in cylindrical coordinates, this could be in spherical coordinates, this could be in any general curvilinear coordinates. Okay. This divergence could be in any general curvilinear coordinates. So, based on the definition of divergence in those coordinates, you have to define a stream function. Okay. Based on the definition of divergence, you have to define a stream function. Okay. And you will quickly notice that you cannot define a unique stream function for general 3D flows. Actually, for general 3D flows, you need two stream functions. Okay. For general 3-dimensional flows, you will need two stream functions, but here we will look at symmetric flows, symmetric or planar flows. Okay. For these symmetric and planar flows, we can actually get away by defining just one stream function. Okay. So, before that, before we define the stream function for symmetric and planar flows, let us just briefly review what happens in orthogonal curvilinear coordinates. Okay. This thing is important to proceed with our discussion. I mean, I could just give you different formulae, but then you will be like, okay, where do they come from? So, that is why I am covering this part. Okay. So, if you look at orthogonal curvilinear coordinates, there are two very important concepts. First of all, how do we visualize orthogonal curvilinear coordinates? The way to visualize them is that you have some set of curves, let us say these are your parallel set of curves, and you have another set of curves which are always perpendicular to the first set of curves locally. Okay. So, this is an example of an orthogonal planar curvilinear coordinate, and in this case we say that the coordinate along these curves is let us say C1 and the coordinate along these curves is let us say C2. There may be some other coordinate which is coming out of the board, and that would be let us say C3. So, we have C1, C2 and C3 as curvilinear coordinates, and we will have E hat 1, E hat 2, E hat 3 as unit vectors along these coordinates. And an important point here is that unlike Cartesian coordinates, this E hat 1 could be a function of these guys. The unit vectors can change. For example, in these curves, if this is your E hat 1 here and this is your E hat 2 here, these are very different at this place. Okay. The unit vectors could change with the coordinate. Okay. And you guys already know a very common example of this, which is the cylindrical coordinate. So, you have a E hat r and you have an E hat theta. So, in the cylindrical coordinates, you have this let us say as E hat r and you have this as E hat theta. As I am moving along theta, both of these are changing. As I am moving along E hat r and E hat theta, both of these are changing. Okay. So, you already know this kind of an example, is just that you have never been shown it in a very general fashion. Okay. But you know that unit vectors can change with the coordinates. It is a very special case when they don't change actually. Okay. Now, in these cases we have to define 3 more quantities which are usually denoted by H1, H2 and H3. These are called metric coefficients, and what they denote is, so H1, H2 and H3, what they denote is that, let us say you take a position vector, a small position vector dr in your 3D space. In that case, how is this dr, how can this dr be written, how can this dr be written using my infinitesimal change in coordinates. For example, if you have dr in a, if you have dr in a planar cylindrical coordinates, how will you write an infinitesimal position vector? How will you write an infinitesimal position vector? What is a general infinitesimal position vector? You will write it as d r e hat r plus r d theta e hat theta. Okay, you will write dr e hat r and r d theta e hat theta. This is how you will write a general incremental position vector or elemental position vector in these coordinates. Okay. So, H1 and H2 here will be, so H1 will be 1 and H2 will be 1 by r. That is what these H1 and H2 are. Okay. These are called metric coefficients and we are going to define them. All of this we are doing, notice, for orthogonal curvilinear vectors. Okay. We are not dealing with a generalized case here. Yes.
How did you get H2 as 1
By comparing with this definition here. So, this is the definition to obtain HIs. Okay. So, dr is dr e hat r. So, C1, C2, C3 are basically r and theta and z, let us say. So, this is, let us say I am not moving in z at all. So, this is dr e hat r by 1 plus d theta e hat theta by 1 by r. So, H2 is 1 by r. There is a very important reason why I am covering this part here, that will become clear to you in a minute. Now, with these orthogonal curvilinear coordinates, we define these quantities. That is, let us say we define the gradient of a scalar as this. Okay, we define the gradient of a scalar as this. Notice that I have I appearing in there 3 times, so I am not using the index notation. I cannot use the index notation, so I am explicitly writing the summation. Okay, this is the definition of your gradient. Curl is defined like this. We won't even let's not define curl for any general, actually general vector. Let us say there is a vector which only has e hat 3 component and the component is varying in the other 2 directions only. Okay, and this is basically related to this assumption that we are looking only at symmetric planar flows. What is this A? It will become clear to you. Okay. So, treat it like a maths exercise for now, that I am defining an A vector which has only E hat 3 component. Okay. Most of this course is just math exercise, but del cross A is basically defined. So, these are definitions, you do not have to worry about remembering them, I am just giving them to you so that later on when we are using them, you understand what I am doing to some extent. This is H2, H3. This should be del by del C2. Okay, and now you should see, or you should at least start seeing where I'm getting at. Okay, you should start seeing where I'm getting at. The idea is to formulate this A such that I can probably define a velocity using this del cross A. Okay, the reason for using a del cross A to define velocity would be that identically del dot u will be 0 then. So, if I can write my velocity as curl of some field, then I have explicitly made sure that the divergence is 0. It is very similar to your potential flows, or we have not discussed potential flows, but it is very similar to saying that a vector field you can write as gradient of a scalar field if you know that the curl is 0. Okay. If I know that del cross u is 0, then you will straight ahead write this as this. You will straight ahead write velocity as a gradient of a scalar field. It is converse of that. If I know that del dot u is 0, then I can straight ahead write, if I write it like this curl of a vector field, then I can obviously get that del dot u is 0. Notice that you don't have to necessarily say this, you could have this, which was the Helmholtz decomposition. Okay, in which case you will say that okay, del dot u is del square phi equals 0, and so this phi should be a harmonic function. If you have a harmonic function, you add gradient of that, and then you can say it in a very general fashion. But if I can definitely write u as del cross A, then definitely del dot u is 0. Okay, and this is what we use to define my stream function in general orthogonal curvilinear coordinates. Okay, in general orthogonal curvilinear coordinates, this is how you can choose a function A to define your stream function. For example, let us take an example of your cylindrical polar coordinates only. So, in your cylindrical coordinates, let us say E hat 3 is simply k cap, okay. C1 is r, C2 is theta. We just saw that H1 is 1 and H2 is 1 by r. Okay. Now, if I define this A vector as H3 times E hat 3 times a psi, which is C1 comma C2, a function of C1 comma C2, then I get that del cross A is given by E hat 1 H1 H3 or H2 H3 del by del C2 psi minus E hat 2 H1 H3 del by del C1 psi. And these are your velocity components in E1 E2 direction. Okay, this is how you can construct a planar flow or a flow that is in only two directions. For example, flow in a plane in Cartesian coordinates where flow is only in x and y direction. You could have a flow in a plane in polar coordinates where flow you are describing is in r and theta direction. You could have flow in a spherical coordinate. For example, if you imagine flow past a sphere, let us say there is a flow past a sphere happening. This is a sphere. So, there are three coordinates, you have r. In spherical coordinates you have three coordinates r, you have, let us say this is your ring. So, the angle of this ring with the horizontal theta, and then where you are on this ring. Okay. Does everyone know how to visualize spherical coordinates? Huh? How is a spherical coordinate usually visualized? So, if you look at an arbitrary sphere, then you can think of it like it's a collection of rings. Okay, it's a collection of rings, and then an arbitrary point in the space you can mark its position vector by So let's say this point on the space. So this point is, so this is your what? This is r. Okay. So it is r away. So let us say this is r e hat r, and then you have to also tell which ring you are on. Okay. So the ring forms an angle, ring forms a cone of an angle theta with this axis. This could be any axis. Okay. It here it is x axis, this could be any axis. It forms an angle theta. So you are on, huh? What? So you are on this, in this direction you are at r times theta. Okay, there is no d here happening, and then on this sphere you could be anywhere on the ring. So that angle is usually called the azimuthal angle, and it is phi. You can denote it by phi, and that phi usually goes from 0 to 2 pi. And what is the radius of this ring? Radius of this ring r sin theta. Okay. So in spherical coordinates, your c1 is r, your c2 is theta, and your c3 is phi. Okay. This r goes from some 0 to infinity, this theta goes from 0 to pi, and this c3 phi goes from 0 to 2 pi. That is what your spherical coordinates are. And in this case, so you can think of what your incremental position vector will be. So it will be simply dr e hat r plus what? What will it be? Same as this row, r d theta e hat theta, and then in r on the ring you will move by radius r sin theta d phi e hat phi. So if this is your c1, c2, c3, then h1 is 1, h2 is 1 by r, h3 is 1 by r sin theta. And so if you define a vector a like this, let us say e hat phi, so c3 is phi, so e hat phi times h3, which is 1 by r sin theta psi, which is a function of r comma theta. Then you can form a velocity using del cross A. You can form a velocity using del cross A and this relation. And that velocity will automatically satisfy the continuity equation. Okay. Now, what I wanted to say is, when you have a flow past a sphere, then flow will not change in the phi direction. If you think about it, it's a sphere. If it's a perfect sphere, then flow will be same at different phi locations on this ring. Okay. If you have a sphere on which there is a flow that is hitting, then on different phi locations there is no difference in the flow. On different phi locations the flow is same. So, the flow velocity is not going to be a function of phi. Okay. And another concept is that you will always have a flow that is normal to phi. The flow will never have any component in the phi direction also. There is no swirl, this sphere is not rotating. If this sphere was rotating about this axis, then you will have some velocity in the phi direction. But if you do not have that, then there is no velocity also in the phi direction. So, this is an example of a 2D flow, 2D being velocity are in two directions, not the flow is happening in two dimensions, the velocity are in two directions. Okay. The flow overall is three dimensional. It is just that there is no velocity in the phi component, there is a velocity in the e hat r and e hat theta direction only. The other word for this is that it is an axisymmetric flow. So, the flow is symmetric about an axis, which is this guy. Okay. So, this way you can define a velocity for spherical coordinates, for velocity for axisymmetric flow in spherical coordinates. Let me just give you one more definition, and that definition is what happens to del cross A. And this is actually defined as minus of E hat 3 H1 H2. It's a big expression, del by del C1 H1 H3 by H2. Okay, so del cross A. So your del cross A had only E1 E2 directions. So another curl of that, you have only component in E hat 3 direction. Okay, so del cross of A looks something like this. And if you have your velocity defined by del cross A, then this is nothing but vorticity, and that is del cross of U, and I am writing the vorticity here. Okay. So, if your flow is in x1 and x2 directions only, if you have an incompressible flow that is happening in x1 and c1 c2 directions only, then your vorticity is present only in the c3 direction or E at 3 direction, okay, which is a special which has a special case in planar coordinates, which you know, if a flow is only in x and y, then vorticity is only in z. This is a more general version of that statement. So, if your flow is axisymmetric over a sphere, flow is only in E hat 1 and E hat 2 directions, which are r and theta directions, then you have a vorticity which is only in phi direction basically. It is very difficult to visualize that vorticity, because then if this is your phi direction, it is like vorticity that is running over the spherical ring, this ring that you have formed. Okay. So, it is very difficult to visualize it, but mathematically that is what you have. Okay. Now, why am I discussing all of this? The reason why I am discussing all of this is that in Stokes flow, we saw if this is our governing equation, then we have del square of omega is 0. Okay. We have del square of omega is 0. We know that by definition del dot omega is 0. Omega is del cross u, by definition del dot omega is 0. So, del square of omega is nothing but minus of del cross of omega. Del square of omega is nothing but minus of del cross of omega. So, if you have this equation for vorticity, then you can convert it into a equation for stream function. Why? Because this omega is del cross u and u is del cross a. So, this becomes an equation which has 4 cross products, and it looks something like this a vector. Okay. And eventually we can simplify it to using this definition of del cross a. Okay. Why? Because notice what happened when I took A only in E hat 3 direction, del cross A also turned out to be only in E hat 3 direction. So, if A is only in E hat 3 direction, del cross A is also in E hat 3 direction. So, you can apply the same formula to this double curl in here. Okay. So, this guy is only in E hat 3 direction, this whole guy is also in E hat 3 direction. So, you can use the same formula here. Okay. And that will help us define what is the governing equation in terms of stream function for these particular Stokes flows. Okay. What is the governing equation for stream function for these particular Stokes flows? And so, tomorrow in our makeup class, we will look at Stokes flow past the sphere.